everyone. இன்னைக்கு நம்ம பார்க்க போற டாபிக் வந்து பாத்தீங்கன்னா about the electric field. Okay? So electric field. So it is denoted by E vector. Now in order to understand this, first நம்ம என்ன பண்ணனும்னா let us consider charge distribution. So we have some discrete charge distribution. Discrete charge distribution. So let us consider this case. So that means what? These charges are now actually source charges. Okay, source charges, and therefore let us take like this some region where the charges are distributed. For instance, let us take this is Q1 and this is Q2 and here it is Q3 and Q4 and dot 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 Qn. So we have n number of discrete charges, that two source charges. Okay, so they are distributed like this. Now let us take a charge called a test charge. We keep at some point here. Suppose there is no force experienced by this test charge, then there is no, that means what? Since there is no force experienced by this test charge, now we can also move this test charge close to this. Okay, because test charge can be moved, right? So the source charges are at rest. Source charges are at rest, but test charge can move from, maybe this charge Q goes from this position to this position. Let us take this position as P, okay, where I keep the charge, test charge Q. Now at this position, maybe this charge, the test charge, may experience a force that is from Q1, Q2, Q3 and Q4. Okay, let us now calculate the force experienced by the test charge because of the presence of these charges. Now how to calculate that? We will use superposition principle, that is principle of superposition. Okay, now what is this? The force experienced by the test charge Q because of the charge Q1, which is equal to 1 over 4 pi epsilon 0 Q1 Q divided by R1 square R1 hat, where R1 is nothing but what? The distance between Q1 and the source charge Q. Okay, similarly we can also calculate FQ Q2. So it goes with the same formula, Q2 Q divided by R2 square R2 hat, and dot 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 FQ Qn for n charge, which is equal to 1 over 4 pi epsilon 0 Qn Q divided by Rn square Rn hat. Now what is this principle of superposition says? The net force, the F net, that is the total force acting on this charge, test charge capital Q, this is equal to the sum of these forces. So I can add these forces, that is the principle of superposition. FQ Q1 plus FQ Q2 plus dot 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 plus FQ Qn. Now I can substitute this in all these formulas, on all these relations. The common terms are 1 over 4 pi epsilon 0 q, that also I can take outside. So the remaining terms are q1 by r1 square r1 hat, q2 divided by r2 square r2 hat, dot dot dot, qn divided by rn square rn hat. Okay, so we can now express the total force as some q times 1 over 4 pi epsilon 0 sum over some I is equal to 1 to n. So this I am writing as a more general expression. Okay, q, and it varies 1 2 3 like that, right? So let us put qi divided by ri square ri hat. So notice this relation, notice that in this relation this part is independent of source charge. Sorry, it is independent of, this is test charge, right? So this is independent of test charge. A test charge I have taken outside. This is a test charge, right? Test charge. So that means it is purely depends on the source charge. So this part, the bracket term, depends only on source charge. Maybe here many charges are there, source charges. Okay, so we can define the force experienced by the test charge, which is F by Q, which is defined as, so let us define this quantity as, by definition it is called as electric field at that point. Okay, so we keep a test charge at some point P. Okay, the force experienced by the test charge Q, capital Q, because of the presence of these charges, therefore they are defined as the electric field at that point. So this is called electric field. Okay, now how will you define electric field? Let us define in this way: the space around a charge, maybe I'll put source charge, okay, in which its influence is felt. Just a minute. Is felt. So this is known as electric field. Okay, so we call it as, it is known as electric field, or simply electric field intensity. Electric field intensity. Okay, now the strength of the electric field, or maybe the strength at any point okay, which we call it as maybe the strength at the point P or something like that. Okay, so the strength of the electric field at any point, maybe I can write in this way: the strength of the electric field at any point is defined by the force experienced by a unit positive charge, which we called test charge, okay, at that point. Let us say at P here, okay. So this is the definition of electric field, and therefore we can now say that suppose I have only one charge instead of n charge, I have only one charge. So let us write down the electric field at that point P. For general case, 1 over 4 pi epsilon 0 summation I is equal to 1 to n qi by ri square ri hat. Suppose I have only one charge, n is equal to 1, okay, only one point charge, okay, then the electric field at that any point. So I have a charge q and I measure the electric field at this point P. Now this is the distance, okay, let us call r, then the unit vector is r hat, then the electric field at this point, P, which is defined as 1 over 4 pi epsilon 0 q by r square r hat, okay. So what we notice is this part, once the source charge is given q, small q, okay, now this part is constant, so therefore this is a constant times 1 over r square r hat. So this means the electric field for a point charge varies like 1 by r square r hat. Magnitude wise, this is E of r, which I am going to call simply E of r, okay, which is inversely proportional to 1 by r square. Now how it varies? For a point charge, if this is r, this is modulus of E vector, okay. So when I put r goes to 0, it is almost very larger distance, okay. So this is very r goes to 0, this is almost infinity, okay. It comes from infinity, very larger value, and it decays like this, and when r goes to infinity, so this is almost goes to 0. So r goes to 0, this takes very larger value, and r goes to infinity, it approaches to 0. So this is the variation of E, the magnitude of E, which is varying like 1 over r square. So this is very important thing for point charge. And notice that this is varying like inverse square, therefore this is also called inverse square field, right? So this is actually inverse square field. Electric field is inverse square field because the Coulomb's law is an inverse square law, right? So this is one important point which I would like to say. And next one is, notice that this electric field, which is a function of only r, is also called electrostatic field. Electrostatic field, okay. So now you can also verify that electrostatic field is a function of r. So this is equal to, the curl of this is equal to 0. That means if curl of any vector field is 0, then we will call it as that vector field is irrotational. Vector field is irrotational. So this is another important thing. So this implies that the electrostatic field is conservative. So electrostatic field is conservative. This is a very important observation. Okay, and why this is working? Because this electric field is proportional to force, Coulomb force. We know that this force is also conservative. Coulomb force is a conservative force. Okay, so F is a function of F by Q is equal to E vector. So notice that this F is proportional to E, electrostatic field. Since this is a conservative field, this is also conservative force field. Okay, so F vector, okay, so this is called Coulomb force. Coulomb force is also conservative force field. So Coulomb force is also conservative force field. So this is another important observation. Now, and one more thing which I like to stress here is, since F obey this superposition principle. See, F obey, the Coulomb force obey superposition principle. That is why it is called principle of superposition. So which means the electric field also obey principle of superposition. Don't forget this. And another important observation is, see, the force field, Coulomb force field obey Newton's third law. The same manner, the electrostatic force, the electrostatic field, that is electric field. So this electric field will also obey Newton's third law. So this is another important thing. Next one is, from vector analysis, we know that curl of any vector field, suppose any vector field is equal to null vector, then if this is satisfied, then that vector field, this vector field which I am writing like here, this vector field can be derived, this vector field can be derived or arrived from a single scalar valid or single scalar field or scalar valid field. Okay, so this is a very important thing. So curl of E vector is equal to null vector, then E vector can be derived from minus gradient of phi. Okay, so phi. So this is called scalar potential. This is called scalar potential or electric potential or electric potential. Okay, or sometimes electrostatic potential, or simply it is called potential. Simply it is called potential. Okay, now in the same manner, if curl of E vector is equal to 0, you will get this. Since we know that this vector field, that is a force field, also irrotational, right? So curl of F vector is equal to null vector, which means this F vector can be derived from minus gradient of, negative gradient of some function that I am going to call V. This V is called potential energy. So this is force field can also be derived from a single scalar function, that is the potential energy. So electric field derived from a single scalar potential, single scalar function, that is called electric potential or potential, whereas the force field, Coulomb force field, can be derived from here force, right? Force can be derived from, if they are conservative, okay, then that is irrotational. So therefore we force field can be derived from a potential energy. And the point which I would like to stress is the electrostatic force is conservative, and therefore the Coulomb force is also a conservative force field. So the remaining things I will do it in the next lecture. Thanks for watching this video.